Here I've tried to redo this picture to a little better scale, and I think I improved it a little bit, but it looks like this parabola is still getting fatter as it moves to the left. And I was pretty careful to rule off these points and make them equally spaced. In any case, you see the 3 points of the original y equals x squared parabola. This would be the y equals x plus 5/2 quantity squared parabola. And then this one shifted downward is the y equals x plus 5/2 quantity squared minus 9/4 parabola. And this is identical to this expression. If we expand this, add things up, simplify them, we're going to get x squared plus 5x plus 4. Now I'm going to summarize what we've seen here briefly on a different board. So hang on, I'll be back with a different board before you know I'm gone. Continuing summary, graphing quadratic function. When you substitute x equals 0, you get the y-intercept. You should understand the logic of that. Now, if you're factoring, if the function is factorable, then you can factor to get the zeros in the method we illustrated. Setting each factor equal to 0, solve for x, gives you the x coordinates of the zeros. The quadratic formula gives you the zeros if they exist, if they're real. Okay? The quadratic formula, as you know, can also give you complex and imaginary results, in which case the zeros would not exist. That would be, for example, the case if your quadratic function looked like this. Now, any quadratic function is going to have a y-intercept. It could look like this, or it could look like this. Neither of the functions represented by these curves will pass through the x-axis, so that when you work through the quadratic formula, you're going to get negatives under the radical. Okay, you're going to have a square root of a negative, and you're not going to get a real number solution. And neither of these, if the function's factorable, you are going to get zeros. It means you're not going to have either of these cases. You're going to pass through the axis at 1 or 2 points. Okay? The quadratic formula gives you the zeros if they exist, and it gives you the axis of symmetry, which is at x equals negative b over 2a. And that's the case whether the zeros exist or not. So, for example, for this function, this is at x equals negative b over 2a for the function that we're representing here. Another thing that I didn't mention is that the coordinates of the vertex are found. All you do is substitute x equals negative b over 2a into the equation to find the y-coordinate of the vertex. So that if we know x equals negative b over 2a and we know the equation, we substitute it into the equation, we get a y value, and that'll give us the y-coordinate of the vertex. And, of course, it'll lie on the axis of symmetry. If we complete the square, it gives us the form f of x equals a times x minus h squared plus k. And this is graphed by transformations of y equals x squared. We have a vertical stretch by factor a. We have a horizontal shift, negative. Horizontal shift is not negative h. Horizontal shift is h. If this is x minus h, because the shift goes in the direction opposite the sign here. And the vertical shift is plus k. Illustrating the axis of symmetry thing, for the function that we did work on, which is f of x equals x squared plus 5x plus 4, has zeros at x equals negative 4 and 1, as you can find from the factors, and can be obtained by a horizontal shift of negative 5/2 and a vertical shift of negative 9/4. If we use the x equals negative b over 2a to find the coordinates of the vertex, negative b over 2a is going to be negative 5 over 2 times 1, which is negative 5/2. If we plug 5/2 in for x, we get f of 5/2 equals this, and we can easily do the arithmetic, and we get x equals negative 9/4. So the vertex is at negative 5/2, negative 9/4, and that's completely in agreement with what we get here, because if we if we shift the vertex of the y equals x squared graph 5/2 units to the left, 9/4 units down, that's where it's going to end up. Okay, just a quick summary of everything that of the tools that we use in graphing quadratic functions with different methods.